Ignite your curiosity with Austin next. We're watching Austin transform from a thriving ecosystem into a global superstar. With our host, Jason Scharf, we aspire to better comprehend the true nature of innovation. Together, we will uncover what makes a successful ecosystem and navigate the technologies shaping our future. Now let's dive into what's next.
Are we overlooking the most powerful model of intelligence we have in our race to create smarter machines? The human mind. My guest today is Peter Voss, a pioneer in artificial intelligence who in 2001 coined the term artificial general intelligence, or AGI. We explore Peter's vision for AI as he challenges the current consensus path we are on. Peter Voss is an engineer, scientist, and inventor, as well as a serial AI entrepreneur and leader. He started in electronics engineering, then fell in love with software. Peter achieved his first major success by developing a comprehensive ERP package and taking that company from zero to a 400-person IPO in 7 years. Fueled by the fragile nature of software, Peter embarked on a journey 20 years ago to study what intelligence is, how it develops in humans, and the current state of AI, while successfully commercializing an earlier version, Smart Action. This research, development, and commercialization culminated in the creation of his proto-AGI natural language intelligence engine called AIGO that can think, learn, and reason, and adapt to and grow with the user. The AIGO engine has already replaced thousands of call center agents in the field as a proof point and is now gearing up to reach human-level intelligence developed on human, brain-like cognitive architecture. Peter co-authored the white paper titled Concepts is All You Need, a More Direct Path to AGI that details this groundbreaking approach to achieving human-level AI. He is on a mission to bring AGI to the world to boost human flourishing. There's a lot of terms that are kind of thrown around. From your perspective, how do we define AGI versus terms like the singularity? Sometimes they throw around like an AI god. Like, how do you define them? What's the difference between them? Or should they be being used interchangeably?
Right, very good question. And I think I'm somewhat qualified to answer that because I actually termed the coin in 2002 together with two other people, and we wrote a book titled Artificial General Intelligence.
Perfect.
So I'll actually give a little bit of background, sort of what got us to even coming up with a new term. The term AI was coined 69 years ago by John McCarthy, and at the time they thought they could crack the problem of human-like thinking and reasoning and learning, to have an AI that can think, learn, and reason like a human. They thought they could crack this in a few years. Now, of course, it turned out to be super, super optimistic, and it, turned out to be a much, much, much harder problem. So what happened in the field of AI, really very quickly, it turned into the field of narrow AI. And there's actually a profound difference between the original vision of AI and what really people have been doing for the last 60 years. Narrow AI really picks one particular problem that requires human level intelligence to solve. And then it's a human intelligence that figures out how to write a program to solve that particular problem. So it's not that the program itself has the intelligence to figure it out. And a very good example here would be Deep Blue, the IBM's chess world champion.
Mm-hmm.
It was the ingenuity of the programmers to figure out what specific algorithms to use to get a system to play a mean game of chess. So it's not that the program itself figured it out in any way. And we're still in that era.
There's more of these rules-based engines, right? We're coming up with these rules and able to do this at kind of a mass scale. I obviously know I'm bringing it down at a technical level, but
correct, yeah. But actually, the same is true for deep learning, machine learning, because it's still the ingenuity of the engineer that figures out how to configure the network, what data, how to prepare the data, how to tweak the parameters, and to experiment and so on. And we're seeing that now, even with sophisticated systems like generative AI, ChatGPT, there's an enormous amount of human intelligence required to actually get these things to do useful things in the real world. To sort of autonomously do something, to set up a RAG and how to train it, and prompt engineering and parameter tuning and fine tuning the model and so on. And then there has to be a human in the loop to basically validate whether it's giving the right output. Now, obviously, it's much more sophisticated right now, but it's still the external intelligence to a large extent that makes things happen.
But I have
So,
a question on that though. When you talk about the external intelligence to make these things happen, but there's a lot of and please correct me if I'm wrong, the black box problem, right? Which we don't understand how some of the decisions are made, or how we may know the weights, we may know,
right.
as you said, the parameters they're going in,
Mhm.
but then we can't explain why XYZ decision was made. So how does that factor in?
Sure, and that's why people have to experiment with it. And I'll be talking later about an approach that isn't opaque, that isn't a black box. So there are actually viable alternatives to it. So that certainly factors in that. But it's still, the point is, these systems cannot learn incrementally. They cannot learn in real time. So and that is what intelligence requires. So, but I really want to get back to your,
Yeah.
to your question of AGI. So in around about 2001, I had just completed 5 years of really deep study of all different aspects of intelligence, epistemology, theory of knowledge. How do we know anything, and cognitive psychology? How do children learn? What do IQ tests measure? How does our intelligence differ from animal intelligence? So on. So I came to the realization that we really wanted to move back to the original dream of AI, to build thinking machines that can think, learn, and reason like humans, which implies also in real time conceptual learning and like children learn. And so I found a few other people who come to the same conclusion. That we felt in 2001 that the time was ripe to go back to the original challenge, that hardware and software had developed sufficiently to tackle that. And that's why we decided to give it a name, to distinguish it from what everybody else was doing in AI. So that's artificial general intelligence, is really to build a thinking machine that can think, learn, and reason the way humans do. An important aspect is you can think, you can learn in real time incrementally. You can conceptualize, so you can generalize in real time. And there's also system one, system two thinking. You have metacognition. You know what you're talking about. You're not just an automatic pilot kind of predicting the next word. So that's really what AGI is. Now, by implication, an AGI will be able to learn any job, any cognitive job that a human can do. But it's a simple implication of that. If you have an AI that has human level intelligence, it can learn to be a programmer, an accountant, a lawyer, any of these things. Leaving aside robotics, so it can't be a plumber or an electrician. That requires
The
development
embodiment layer, right?
on robotics. Now, so to get to your question of how does that differ from the singularity, again, by implication, it means that the system can be an AI designer. And an AI inherently has many, many advantages over human cognition. And, we can go through them, and I can list them. But inherently, from a problem-solving ability, AIs are inherently much more capable than humans once you get to that AGI level. So clearly, they will be able to improve themselves. And
Mm-hmm.
that's really, I think, the meaningful definition of the word singularity, the time when you have a computer system that's smart enough to improve itself. And it will then get smarter and smarter up to some kind of theoretical limit, presumably, or some limit of resources that it might have, and so on. So that to me is the singularity. Now, getting to godlike, I think there's a deep misunderstanding, and even the singularity, I think there's a deep misunderstanding that people often extrapolate that and say it'll have infinite intelligence, or,
Right.
I mean, godlike implies that it's infallible, omniscient, and that's complete, utter nonsense. We know scientifically, we know that many, in fact, most problems in the real world um, do not have exact solutions. I mean, for example, it will never, ever be possible to predict the weather exactly in one particular location a week from now,
Right. Yeah.
because of chaos and because of quantum uncertainty and so on. We actually know that now, that it's not, the future is not predictable, basically.
I
And
was joking even here in Texas. Like when somebody says it's going to rain, I
yeah,
believe them. If they say it's going to rain at 2 o'clock, I almost say I can guarantee you it's not going to rain at 2 o'clock, but it's
right,
going to rain somewhere around that time
right.
because the storm is coming.
Right. Yeah, actually, where I live here in Austin, it's kind of a joke that I have like a protective dome. Then, when there's rain all around us, it never seems to come over our house. Um, so, but
My house does
you
not have that dome.
okay. So, we know theoretically that most problems in reality, like predicting biological systems, are simply not ultimately tractable. So we're never going to have a godlike AI in the sense of being omniscient and infallible. That's just not possible. And similarly, the singularity does not imply an infinity, that intelligence, any kind of intelligence, will top out at some level. Now, we don't know what that level will be, but clearly there are problems that are, infinite orders of magnitude, or many orders of magnitude, harder than any AI will be able to solve, because it simply won't be able to model things accurately enough. So, AGI, yes, there will be the self improvement of AI, get smarter enough, basically, and I jokingly say that I know AI will take over my job, because as AI gets smarter and I get dumber, there'll be a point where the two cross over. So hopefully I won't be all that dumb by the time that happens.
So
So I don't know. Does that make sense?
it does, but I'm wondering, almost like chicken and the egg here, is the singularity, when hearing it, is the singularity is AGI required for the singularity, or vice versa? Because does the singularity just mean a AI that can improve itself, and does it require human level intelligence to be able to improve itself? Or can you
Uh,
have something that has a level of intelligence that can improve it? Like that, do you see what I'm saying?
yeah. I see what you're saying. Um, no, I believe to be able to improve itself, it needs to be able to understand the theory and so on. And so it's going to be human level in general intelligence, to do that. There are. Um, there are obviously self-learning systems, like um, what AlphaGo, and that basically can use brute force to try and improve their algorithms, and then as those algorithms get better they can improve. But they're not general intelligence. They are all big data, bulk learning systems. They cannot learn incrementally. So I don't see that as a path uh, towards the singularity. It really needs to conceptually understand design to be able to make improvements. It can't just sort of blindly experiment and try and tweak parameters. There are just way too many parameters to tweak for us to get to human level intelligence, sort of just by brute force.
So we're kind of talking in many ways here, kind of in the abstract.
Mhm.
How do you measure it? I mean, I know we used IQ. We see a lot in the current LLMs. They use a lot of these kind of tests,
Right.
right? The MCAT, they kind of these tests. What is the benchmarks? What's the measurement? I kind of joke that back in the day we used the Turing test, and
Right.
we've
Right.
we've pushed that away. Like people are very easily kind of fooled by
Right.
machines now into being humans. Now, in some cases, if we say I've seen a lot of tests recently where that we think that some of the machines versus say doctors, the machines are more empathetic. So you actually might be like, oh, maybe the Turing is a positive test and more of a negative on the human beings themselves.
Right. Actually, I just want to before I answer that, I just do want to go back on the singularity because
Yeah.
people might violently disagree with the statement I made. Um, there's also a very common interpretation of the singularity that when things change so rapidly that we have no visibility of the future, that basically the sort of event horizon, that things happen that change that quickly,
Mhm.
that we will not be able to predict the future. I don't think that's particularly useful, because to what extent can we predict the future? And so to me, the alternate definition of the singularity is when a computer reaches a level of intelligence where it can improve its own design autonomously. Anyway,
Mhm.
getting back to your question, yes, I actually many years ago I wrote an article on the Turing test and how valid it is, and I think it asks both too much and too little in different ways.
Hmm.
It asks too much in that it expects you to play dumb when you say, divide, two 8-digit numbers, and it'll come spit out an answer immediately. It needs to play dumb basically in the things that it's good at, but it also asks too little in that you could, and people have obviously done that. You fine tune a system that's really good at fooling human judges,
Mhm.
and then it can kind of win the Turing test, as supposedly it did already 5 years ago or 10 years ago or whatever. So yeah, I think the Turing test is not particularly useful. So how do we know that we getting there? And this is really at the question of understanding intelligence. And a lot of people kind of say, well, we don't really know what intelligence is. Uh, well, if that's a starting point, then yes, you're going to have a problem judging whether you're building an intelligent system. And I think it's really important to
Are we going back to the
understand.
Born test, like with Brandon? I'll know it when I see it.
Yeah, I know. Yes, that in fact I had the exact discussion where I said, to build an intelligent system, you really need to understand intelligence first to be able to build it. And the person said, well, nobody understands what intelligence, or nobody can define it. Intelligence is as intelligence does, but that's like fortune cookie philosophy. So understanding what is really special about human intelligence, and this is why it was so useful for me to study what IQ tests measure and how children learn, and all of that. Um, the unique human ability is for us to be able to form concepts autonomously, that we can generalize things, and we can form very abstract concepts on top of concepts, getting up to things like honor, which is a very, very abstract concept and depends on a whole lot of lower level concepts. Animals can't do that. And you need to be able to do that in real time to be able to evaluate new knowledge that you come across, like the conversation we're having, or you read an article. You need to basically analyze automatically every sentence you're getting. Is this something that I already know, that I agree with? Is it something I disagree with? I'm not sure. Is it something I understand? Am I confused about it? Does it make me think of something else? So we integrate knowledge interactively, and we may ask questions. We may, ask for clarification, or may make us think of something else. And then, as we get multiple examples, we can generalize and form generalizations, and we can use those generalizations in different domains. That's basically transfer learning. And so it's those abilities, including our metacognitive ability, or what Daniel Kahneman calls system two thinking,
Mhm.
that we can reflect on our own thought processes and direct those thought processes. Now, of course, with recent LLMs, people are kind of trying to do that by having LLMs spit back their answers, back as input to try and force them to. But it's not really. There's not this conceptual understanding of what they're doing, or what they know, or what they don't know. But of course, it becomes pretty blurry at that point, on whether something is metacognition or not. But for human intelligence, that is really important. But to me, the key is real time interactive conceptualizer learning, and conceptualization is really key to it. If you hired a personal assistant that say knew spreadsheets and knew a whole lot of things, how to do things, but they couldn't learn in real time. So you have a new product release, you have a new customer, something changed, you shut down a division or something. That information and all of the implications through that need to be integrated straight away. Otherwise, next day your assistant doesn't know anything new. Then that's not very intelligent.
Okay, I'm going to ask. This may sound like a really basic level question,
Mhm.
but I know that there's been the recent advancements in OpenAI with like the memory concept. So
Mhm.
I've entered in and I built in memory so it does integrate. It's not, to your point, it's not real time. So like I'll put that a sense, but it is okay. I'm going to use learning here, but I'm putting up quotes here that
Mhm.
I understand.
Right.
It's not
Right.
real
Right.
time learning. Isn't that a step closer? I know we heard of what we can. I'll give you a chance to beat
Mhm.
up LLMs a little bit in a
Right.
moment. But isn't that closer in that because they are learning, they are getting memory. I saying like, look, I prefer. It's the simplest thing of saying stop using the word delve. I hate
Mhm.
that word. Don't put that in when you're using writing. Stop using that. So it learns to stop using that word. It may not always listen. It's not kind of
Mhm.
perfect, but isn't that a form of learning? I know it may not go into the deep training data.
Right. Yes, the core model doesn't get updated. So, and and this is all. So there are basically two ways in which people try to deal with this inability to learn. The one is to use bigger input buffers and to give it, all of these pre-prompts of what you should do or shouldn't do, and it can learn those. Up to a level. The problem is that does not update the model at all. So it's like a list of stuff that you have in there that the system hasn't integrated. And there are, severe shortcomings. I mean, tests have shown that typically it tends to pay more attention to the stuff that you said recently or stuff that you said right at the beginning, and there's like a hole in the middle. But the bottom line is it does not update the model, and there are implications. And of course, the other problem is every time you shut the system down, it forgets it. So then you're gonna every time feed in 500,000 words as a prompt just to use the system again. So it's a hack. It's a patch,
Sure.
and it doesn't it doesn't integrate that information. Now, the other way, of course, is people use RAG. They use external databases, but they also they have to be structured in a certain way. They have to be specifically engineered, and they're only as good as a system's ability to recognize that a particular prompt should call the database, and then and hopefully call the right vector to get back the right information. So that's pretty shaky as well. It's not terribly reliable, and it's it's slow. And as I say, it really has to be structured information that is fed in manually. So you really want a model for true intelligence. You really need a model that can learn truly in real time. And in fact, I co-authored a paper recently where we did a review of recent research and people trying to get systems to learn in real time, large language models to learn in real time. We surveyed more than 200 papers that we reference in our white paper. Not a single one updated the model in real time. Nobody is even attempting that. And GPT, the P means pre-trained,
Mhm.
and the T is transformer, which is the magic that makes these things so incredibly powerful. But T, also transformer architecture, also commits you to backpropagation, which basically is bulk training. It commits you to this pre-trained and read-only model. So really true intelligence needs to be able to conceptualize and update the model. There could be something like a scientific paper that you come across, and suddenly that was retracted, and all the implications of what that changes
You
in
can't just
in
go in
knowledge.
and
Yeah.
pull it out in a simple way.
Yeah, and you can't do that with large language models. um, Now, the other thing is, so obviously they're chipping away at at the problems of it, but also at a huge cost. Now with the reflection on the latest release that came out yesterday, you're now looking at between 10 and 50 times more inference cost and time. So now you're looking at a 10-second response. Now, obviously, in a few years' time, that'll speed up again, but then models will get even bigger and the inference will get even bigger. So it's kind of absurd that people are just blindly pursuing that avenue because it's got momentum. When we know, when you go back to first principles, our brain uses 20 watts of power, not 20 gigawatts, to learn everything. A child can learn language and reasoning with maybe 1 or 2 million words, not 10 trillion or tens of trillions of words. So there's something very fundamentally wrong in the approach we're taking. It's sort of, we have a lot of data, we have a lot of computing power, and our partners, NVIDIA and Microsoft, obviously would love us to use even more computing power. So let's do it. That's a hammer we've got. So let's see what nails we can find.
But
when it's kind of an absurd, from first principles point of view, it's an absurd situation.
let's steel man it for a moment, because I've heard, not being someone who's not obviously not steeped in this technical and at this level as you are and many others, that I've heard what you've said before, and many like you in this, that clearly our brains and there's a reason we called it neural nets, right? We were going after the way that we thought,
right?
That there was that was the approach, right? Think about the way the human brain works, and these mass scaling and the way that we've done it, these mass numbers, these data centers has produced amazing results in the last few years. I mean, you look at just like Tesla, right? Tesla was the more rules-based methods, and
Right.
since they've thrown that out and gone to, and I think it's an overstatement, but gone to this Gen AI method, and their self-driving has just gone leaps and bounds. So while on a first principles method, clearly we're missing something, to your point on that, between we are able to, as humans, and our brains are able to do something different on it, but that doesn't say that the way that we're doing this at mass scale and with the chips and mass data isn't producing some amazing results in this current path.
Right. Absolutely. I mean, it is producing amazing results. No doubt about it. I mean, when ChatGPT came out, I don't think anybody in the field expected it to be as good as it is, and to be able to do the things. I think it was a total shock of what you could achieve with scaling. But that was 2 years ago, more than 2 years ago now, and it really hasn't advanced that much in terms of the kind of errors that it makes, and so it the 10 times more processing power certainly doesn't give you the improvements are much less, or it seems to be plateauing. So yes, absolutely, it can
Granted, the
do
model,
amazing things. Yeah,
the Model O or O1 has been out for less than 24 hours, so we'll see how that one plays out.
Right, but yes,
I'm not disagreeing with you, and I am steel man, but
right.
it is interesting. I do laugh at that a little bit when you say it's been out for 2 years, and I said I'm not disagreeing on
no,
on first
ChatGPT has,
principles. No, I said the ChatGPT has been out for 2 years, and we're all like, all of us are sitting there like, why isn't it doing more? And it's like, wow, that's how fast it's amazing to me. I've had this discussion many times, how fast our integration of technology mentally has been, with like this what was kind of that pre and post moment of ChatGPT, and it's from the like, I can't believe what was before is like, this isn't possible, to now it's like, where's GPT-7?
Yeah. Well, I think a good question to ask is, how useful really are these things? And actually Tesla doesn't, apparently, according to Elon Musk, they don't actually use transformers for the system. They use, deep learning, machine learning. And actually, just talking about it, there's still a profound difference. There are these edge cases, many edge cases, and I love Tesla. I've owned a Tesla for 6 years. I've seen the improvements of full self-driving. I still don't use it other than on the freeway because it's too frustratingly timid and slow. To do things. But yes, it certainly has improved. But again, it's not like human intelligence where, we might get into a new neighborhood and we learn that going around a certain curve, there's a driveway a blind driveway that somebody reverses out of,
Right.
and we learn that. It might happen once to us, and then, oh, okay, I know I need to be extra careful here, on this. They cannot do that they cannot learn in real time at all. They cannot adapt. Now again, they're doing smart things to try and overcome that by, I think they now have a program where they want to crowdsource if one Tesla drives by a place where there's a construction site or so that, it's new,
Right.
then they can spread that information out to other Teslas. I think that's something they're trying to implement. So there certainly are good workarounds. But if you look at generative AI in particular, and you look at practical use cases 2 years later now, and enterprise companies have been throwing enormous amounts of money at trying to use ChatGPT usefully, and it's actually very, very little that is useful. And my own company, we have experience in call center automation, and a system that is 95% reliable, or even higher percentage. Once if you're in a customer service call where you might have 5, 6, 7, 8 steps you have to go through, by the time you go through 6 steps with 95% accuracy, it's a complete disaster. And so there's enormous amount of human engineering required to put in all the guardrails and the checks and fine tuning and whatnot, that at the end of the day it's sort of tail wagging the dog, that you may as well just had simpler technology that is more robust to do the job. There really aren't a lot of good use cases for generative AI.
What do you think? I don't know if you heard about this or not, but Klarna just ripped out Workday and Salesforce to replace it with a Gen AI stack.
Well, maybe they just ripped them out because they weren't working very well. Doesn't mean that what they're doing now is going to work any better. So the question is,
fair, yes.
Why should we pay for? I mean, to me, that's an indictment of Gen AI. If a company like Salesforce can't produce a product, that that gets ripped out, so you can look at it both ways. But I think something else that I think you're alluding to that's worth talking about is, rule-based systems clearly weren't the answer. I mean, they were brittle, and going to a statistical system clearly is a major advance in speech recognition and translation and image recognition. It really made self-driving, or getting close to self-driving, feasible. But what I believe the answer is what DARPA calls the third wave of AI. And what DARPA, they gave a presentation a few years ago where they talk about the 3 waves of AI. And the first wave of AI is what we now call good old-fashioned AI. Essentially the stuff they did 70s, 80s, 90s, largely rule-based systems, expert systems. Deep Blue would be a perfect example of that as well. That's the first wave. And then the second wave hit us like a tsunami about, I don't know, probably 13 years ago now, when people began to figure out, when they figured out how to actually get neural networks to do useful things by companies having large amounts of data and massive amounts of data and massive amounts of computing power, and tweaking the algorithms a little bit, and then deep learning basically suddenly produced these really significant advances in image recognition, say, and speech recognition, translation, and stuff like that. And that's still the second wave. That's a wave we're still surfing right now. But what DARPA referred to as the third wave is adaptive systems, basically systems again, coming back to to the importance of real-time learning, systems that can learn and adapt in real time to changing circumstances. And that also implies that they have understanding, that they can generalize, they can conceptualize. So the difference here is the key to intelligence, and this is a very common misunderstanding of intelligence. The key to intelligence is not how much you know, it's your ability to acquire knowledge. And large language models know way more than any human, in terms of knowledge and also skills. Some of the skills, some of the things they can do, they're way off the charts, way more than any human could ever know. But their ability to learn in real time is zero, basically. So real intelligence, the focus is on the ability to learn. And you can see that in children. I lived in Africa for many years, and a very good illustration of that is you might have somebody come from rural Africa that didn't have electricity, that never seen a car, kids that grew up there, and then they go to the big city, and it's that inherent human intelligence that they have, how quickly they can adapt to big city life, to electricity, to laundromats, to taxis, to jobs, whatever. And it's not what they knew before. They had the intelligence, they didn't have the knowledge. The intelligence was the ability to learn, to integrate, to generalize, and to reason about things. So once you understand what is important in intelligence, then you can kind of see, well, it doesn't matter how much more money you throw at training the system with more data or more skills. You're not addressing the fundamental problem. It's like you're trying to go north, but you're pointing east. It doesn't matter how hard you go east, you're not going to get north.
Of course, it's funny, that entire description is a big, I don't want to say indictment of the way we do schooling, but so much of it is about knowledge transfer versus understanding and reasoning transfer.
Yeah, the ability to think. The ability to actually think and learn. I agree.
Especially since the amount of, let's put, data information is so increasing. And what's also increasing is our ability to get it. So we can get it all in real time and pull it together. And that is a skill. So you learn how to get the information. But then what you need to do is then, okay, what do I do? How do I put it together in unique and interesting ways? That's the thing I'm trying to teach my children, and I want them to learn at school, not necessarily XYZ date, XYZ. Those things are actually simple to get now.
Yeah, absolutely. It's not the knowledge that's going to make you operate in the real world. It's the ability to learn new things and to adapt to changing circumstances. And things are going to be changing more and more. And people who can learn and adapt are going to be able to do much better.
Well, and it's funny actually how much we realize. So my kids are elementary school age, and how much we've had to adapt to the software that's out there, because so they've obviously now very much used to ChatGPT. And my oldest has been doing a project, and they said you for the research you can't use AI. You have to go get a source. You have to use Google, and it's been quite frustrating for him, because you realize all the ways he does queries, when he asks questions, are designed for AI. He doesn't ask questions the way we all got used to asking, like basically keyword searches.
Right.
And so he sets it up as like full questions. Like, Google doesn't know how to do that. Like, I know now it's doing things like Gemini, but so it's been really interesting to see. And you step back, you're like, man, that was a dumb way that we searched for information, when it was much better to just say, like, tell me this piece of information. He was looking for, like, what is the cheapest material that does X, Y, Z? Well, that is not a way that Google is set up to answer that question.
Right. But I mean, the technology just didn't exist. I mean, Google is phenomenal, of that. But yes, you absolutely needed a lot of human intelligence, especially once they started adding all those ads that you had to, ignore to
Yes.
get to real information. So yes, it's very much human in the loop for, both for Google but also for large language models is very much human in the loop. And so this third wave of AI, and a good way to describe it is to call it cognitive AI, because it starts with understanding cognition and to build a system that can learn. And the byproduct of taking that approach is that you need orders of magnitude less computing power and training data, because the system can learn like a child. A child may be exposed to a few million words before they not if that before they get language competence and basic reasoning ability. And so building a system on the third wave approach that is inherently real-time, adaptive, and learn in real time, you simply don't need hundreds of millions of dollars to train the system, or tens of trillions of bits of information that you found somewhere.
So obviously, the word cognitive is coming from cognition, same kind you had like neural net. So what's the difference from a technical perspective, the way we used to do? Because again, we heard that same bit of train off the way we do it, our
Mhm.
brains work. So how is this different than what was tried before, or
Right.
is it just an offshoot of what we figured out something different?
Well, how the brain works is, I think, actually a different approach.
Oh, okay.
There's a difference between how the mind works and how the brain works. And there, a
And
good
we haven't crossed
analogy
that
is,
chasm yet to bring the two together. Yeah.
right. Certainly, one can get inspiration from the way the brain works, but there's a difference. And I think a good analogy there is that we've had flying machines now for over 100 years. We still nowhere near reverse engineering a bird.
Mm.
So it's basically trying to understand how the mind works rather than how the brain works, and this is really how does intelligence work. And the kind of key things there are the ability to form concepts. This is one of the key aspects, and I can't touch on all of the key all of the important mechanisms of how the mind actually produces intelligence. But one of them is concept formation, is basically the ability to generalize. That's key. And you need to build a system that can do that in real time. You can show a child even a single picture of a giraffe if they've never seen a giraffe before, and it'll be able to recognize a giraffe, from the top, a pink one, and from the side, a small one, big one, and so on. So you don't need thousands of examples of that, and so you need a system that can generalize with much less information, much less data. You need ultimately metacognition, a system that can think about its own thinking and adjust it accordingly. In fact, my study of psychometrics of IQ tests, I was quite involved for about a year with a new type of IQ test in South Africa. And one of the interesting things that I learned is that metacognition, the ability to think about a problem in the right way, is actually the single biggest indicator of general intelligence and general competence in humans. So, some problems require logical thinking, other problems require a reliance more on memory. Yet other problems require you to take a more intuitive go at it. They don't, they don't, they're not, they can't be solved with pure logical thinking. You need to kind of have a more holistic. So our metacognitive ability is basically to subconsciously or consciously adjust our mental processes to the situation at hand, to the problem at hand. So those are some of the key things required for cognition. So it's understanding the mind, not so much the brain, and then building systems. Now, how does this differ from stuff that's been done before? I don't actually know of much work. Probably the closest we come to it, there are cognitive architectures that a couple of cognitive architectures that have been around for a few decades that have tried to use that approach where you have short-term memory, long-term memory, reasoning, and so on. But by and large, they had a couple of severe shortcomings that we've overcome in our design. One of them is that they tend to take a very modular approach. So, for example, when they want to do language, they will say, well, what's a good language parser? Or maybe we'll use the Stanford language parser. So that's one module. We need reasoning, so they'll find some reasoning module. We need a data representation. They use some graph database. But they have all these modules that really don't talk to each other, that are separate. So it's like a pipeline. That's not how our mind works. Our mind, as we try to make sense of a sentence, like parsing it, we need to have immediate access to our short-term memory, our long-term memory, to our reasoning. Does this make sense? Does this interpretation make sense? And that all happens in a very highly integrated way. So, we overcame that by designing all of these components ourselves, that they can actually work together with each other. And another innovation was to have a graph database that is actually 1,000 times, literally 1,000 times faster than any commercially available graph database. So it required the high performance knowledge representation and the various cognitive modules or algorithms to be deeply integrated with each other to actually make this work. So, it's like neural networks. For decades, people say they didn't work. Well, they didn't work until somebody got them to work, with deep learning, machine learning. And sort of in a similar way, I feel that cognitive architectures, well, yes, they haven't worked until somebody gets them to work. And I think there's a not, kind of a related issue. You may have heard, it's pretty common now that, in fact, even Sam Altman just yesterday with a release, or in the last few days, said that scaling large language models are not going to get us to AGI. He actually said that we need some new breakthroughs. Jan LeCun, the chief scientist at Meta, at Facebook, put it more strongly. He said that large language models are an off-ramp to AGI. They are a distraction, a dead end. So he put it pretty forcefully, and I would actually agree with him. So if large language models can't get us there, then the question is, well, what can get us there? Can we get to AGI? Can we get to true human level intelligence? So what people are thinking about is, well, large language models can do a lot of things, but they're really not robust thinkers. Their logical thinking is faulty. So can we use more traditional logic systems? So people are talking about neurosymbolic architectures. That is actually a fairly hot area of study, and there's a big conference every year, neurosymbolic. So what people are trying to do then is to take the power of basically wave 2 AI, deep learning, machine learning now, and generative AI, and combine it with good old-fashioned AI, logic systems. But the problem is you end up with the limitations of both systems. You can't just simply try to glue them together. Logic systems are very brittle, and that's basically why they really weren't that super useful. And large language models, well, we've spoken about the limitations, the problems. They can't be updated in real time, and the sheer the hallucinations are very much inherent, and so on. So you really can't just take the two technologies and try and glue them together. You really need to have an integrated system that has both the neuro way of encoding, basically sort of vector encoding of information, and have that combined with the ability to reason. And that's, again, how our minds work, how our brains work. We don't have different structures. System 1 and System 2 are a useful abstract way of looking at it, but in reality, System 1 and System 2 interact seamlessly.
Right.
They use the same knowledge representation. And so our approach is what we call INSA, Integrated Neurosymbolic Architecture, where you have a common knowledge representation, a vector knowledge representation, that can both work at the sort of neurotype pattern matching level, and it can work at the symbolic level, the way humans can.
one of the things we've seen with like the LLMs and the scaling require the, the NVIDIA breakthroughs and the GPU breakthroughs. Does cognitive require similar semiconductor or chip or some sort of like hardware level breakthroughs as well?
No, not at all. In fact, one of the really encouraging things in AI to me is that ChatGPT has sort of shown us that we probably already have enough hardware
Mm.
power for human level or close to human level capabilities. It's just incredibly inefficient because the system has to number crunch through 10 trillion or tens of trillions of tokens to come up with an answer. And so, because cognitive AI properly implemented can truly learn incrementally, it can learn essentially one sentence at a time or one input at a time, and build its model like that. The power requirements and both the data and power requirements, compute power, are many orders of magnitude less.
But is it again, not in
Mm.
chip design or anything? Are there different types of requirements, different ways? Is it parallel? I'm just
Yeah, we
wondering, are there different
yeah.
requirements
The
for
answer
instance?
is we don't know yet. I mean, there's very little work actually being done in cognitive AI, and we can talk about why that is. When I talk about all of the advantages of cognitive AI, why isn't everybody working on it? And it certainly is a big bit of a mystery. Um, but the answer is I don't know yet. The level of system that we've built up to now has had a few million facts um, in it, which for many applications like call center, call center support is sufficient for that to do that. And in fact, in terms of the number of words that an educated human knows, they're about like 60,000. It's not actually a huge number, but we clearly haven't scaled it up to the kind of common sense knowledge and skills that a smart adult has. So we don't know where the bottlenecks are going to be, but we don't have any hardware constraints right now on the devices, and we haven't even optimized much. We're not using GPUs at all. So we haven't even tried to use GPUs. So we have several orders of magnitude of improvements with existing hardware that we can make as we scale up the system and need more computing power. So clearly, once a design of a cognitive architecture, a cognitive approach or neurosymbolic architecture has been um, perfected, is at a point where you really want to commercialize it, you will better understand where the bottlenecks are in computation, and it may turn out that GPUs will be useful to do that optimization, or it may be that you want something like an FPGA, field programmable logic array, basically some kind of a custom chip that's optimized to the particular algorithms that are the bottleneck in your system. So I don't know, but whatever hardware is required, it's going to be many orders of magnitude less than what these large language models require.
Hmm. Yeah, Jensen doesn't want to hear you say that, or at least like,
I
the
I,
chip makers don't want to hear that.
I know, I know. Um,
Something that I kind of want to take a slight tangent here, but I find it interesting. Something I've discussed a lot on the podcast is I think there are first principles with ecosystems. And when you have these kind of stacks of the idea, the companies, the capital, the ecosystem, when they all align, that's when you have real generational outcomes. And I know that you've come to Austin relatively recently, and I think it's fantastic that you're here. And one of the things that I've generally said, though, and I want to kind of hear your thought process, is when I say, oh, if you want to do foundational AI development, my usual answer is get your ass to San Francisco. Like that makes more sense. Um, so what is it then that from your perspective, why come to Austin and not go to the more traditional spot for AI development? And then what have you found kind of in Austin for that vertical?
Mm. Right. Well, I'm actually not sure that going to the Bay Area would be beneficial, because you do have this monoculture and this groupthink there.
Mm.
And I think it's extremely hard to break out of it when people have invested their livelihoods and everything in the big data approach. It's very difficult to break through when as a VC, you've made hundreds of millions of dollars worth of bets in this direction to even listen to something that might be uh, might be completely different there. And even the
You want to be one of
skills,
the rebels, come here.
right? Yes. So, and even the skills that you find in the Bay Area are going to be deep learning, machine learning type of big data kind of skills. And of course, they're horribly expensive there as well. But we don't need people like that. So
Hmm.
we need smart people that. If we took somebody from OpenAI or DeepMind or something like that, they'd have a hell of a lot to unlearn. You know,
Right.
so they're really not very useful to us. Now, the reason I came to Austin was actually because I like the weather here. Having lived in South Africa for a long time, I like hot weather, and I can't stand the Bay Area. Now, to my detriment, because if I'd moved to the Bay Area 20 years ago, I'm sure I would have had much greater funding, much easier funding than I've had over the last 20 years. But I wasn't willing to pay the price to live in the Bay Area. So Austin, I was really very pleasantly surprised coming here. I didn't expect that, of how much AI activity there is. I think outside of the Bay Area, this is probably the next biggest center of activity in AI. We have just um, the recent Austin AI initiative that's been formed, and there's a lot of energy behind that. And just generally, I mean, there are meetups here where 100 people show up at a meetup, an AI meetup. There's several meetups like that. So there's really a lot of interest. Obviously, most of it is generative AI. People trying to implement it. What is missing here is you really have very little VC activity.
Oh, interesting you say it. So my view on the AI is I think our powers lie in the intersection of like I just put it like the digital and physical. So you think about like
Mm-hmm.
Spark Cognition is
Mm-hmm.
AI for infrastructure, right?
Mm-hmm.
Or you see Saronic, right? There are software and autonomous vehicles for defense tech, or Icon is using AI. So it is that application layer and using AI. I think
Mm-hmm.
AI, to your point, I think AI is very big here. It's when I think about the kind of the fundamental layers. You see a lot of the VCs. I mean, when you think about, we're like the fifth largest, depending on the fifth or sixth largest VC market in the country. It just depends on where it is it's going into. So it's a very interesting and dynamic environment. But what it is in the particular first principles that we're going for. So, but yeah, it's a really interesting
Mm-hmm.
interesting state of kind of where we're at.
Yeah, I hope that Austin becomes the hub for cognitive AI. I mean, that would be awesome. But also with COVID, our company basically, instead of having everybody come to a single location every day, since COVID, we started hiring people all over the world, and we are actually now distributed. I'd love to hire more people in Austin. It's still great to be able to get together at least occasionally to brainstorm things and build more of a community. And so I look forward to that happening. But of course, the vast majority, pretty much all the AI activity is around generative AI. Of course, that's what gets funded.
Yeah, it's one of those things. It's everything. You're contrarian until you're not, right? And then
Yeah,
it's
right.
always
Exactly.
being
Yeah.
being the first of the wall is the one that gets bloodied.
Right. Yep.
Now, Peter, this has been a lot of fun and really deep and understanding. So I always end with the same question. So then, what's next, Austin?
Well, as I said, I hope Austin becomes the center of cognitive AI and AGI, because AGI directly is a direct outflow of properly implemented cognitive AI. systems that can think, learn, and reason like humans, that can learn like children, from the ground up. And we don't have to build new nuclear power stations and build $5 billion data centers for that, and the environmental impact that has, and all that. We don't need it. We just need to step back and say, do we really want to keep plowing all this money into a dead end, a distraction?
So what's next, Austin? We're glad you've joined us on this journey. Please subscribe at your favorite podcast catcher, leave us a review, and let your colleagues know about us. This will help us grow the podcast and continue bringing you unique interviews and insights. Thanks again for listening, and see you soon.